Tonight, we're going to explore something that keeps astronomers awake at night, staring at their data in silence. The Great Silence. You've probably heard about it before. It comes up every time someone mentions alien life or the search for intelligence beyond Earth. But here's what most people don't realize. The emptiness isn't just strange. It's so statistically unlikely that it demands an explanation. And every explanation we've found so far is unsettling in its own way. And by the end of this journey, you're going to understand why the silence might be the most important mystery our species has ever confronted. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. When you step outside on a clear night and look up, you see stars everywhere, thousands of them, scattered across the darkness like someone spilled diamonds on black velvet. The sky feels crowded, full, alive with light. We think of space as being full of stars. Actually, that's not quite right. Let me try again. We think of space as being full of stars because that's what we see. But what we see is a lie, not an intentional one, just a consequence of where we're standing. Here's what's actually happening. On any given night, from any point on Earth, you can see roughly 5,000 stars with your naked eye. That sounds like a lot. It feels like a lot when you're lying on your back in a field watching them. But every single one of those stars, without exception, exists within about 1,000 light years of where you're standing. The Milky Way galaxy is 100,000 light years across. You're seeing 1% of it, less than that, actually. You're seeing a thin shell of nearby stars wrapped around you like a fence. And here's the part that changes everything. When you look up at the night sky, you're not seeing the universe. You're seeing a thin shell of local stars wrapped around you like a nearby fence. The actual universe, the one where the real emptiness lives, is invisible. You've spent your entire life looking at space without ever actually seeing it. The void isn't out there somewhere. It's everywhere. We're just standing in one of the few places where something exists to block the view. Think about it like this. The night sky is like looking at a chain link fence from inches away. You see metal everywhere and think the fence is solid. But step back and you realize it's 95% empty air. We can't step back from our position in the galaxy. We're pressed against the fence, seeing only the links. Every star you've ever seen with your naked eye is in your immediate cosmic neighborhood. You're essentially looking at your own street. The vast universe beyond isn't visible, not because it's empty, though it is, but because the stars there are too far to see individually. They blur together into faint smudges we call galaxies, or they disappear entirely into darkness. The space between stars in our neighborhood averages about 5 light years. That's the distance light travels in 5 years, moving at 300,000 kilometers per second. To put that in human terms, if you started traveling at light speed right now, you'd pass the moon in 1 second. You'd leave the solar system in hours. You'd cross 5 light years in 5 years, obviously, and you'd find nothing, just empty space, cold, silent, dark. Here's another way to understand the emptiness. If you could travel in any random direction at light speed, you'd have to go for millions of years before hitting anything. Not millions of years to reach another galaxy. Millions of years before your ship would physically collide with an object, a rock, a planet, a star, anything solid. The stars we see aren't evenly distributed. They cluster in galaxies because gravity pulls matter together. But even within galaxies, even in our relatively crowded neighborhood, the distances are staggering. If you drove from the moment writing was invented, about 5,000 years ago, until now, driving without stopping, never sleeping, never aging, you'd still be inside our own galaxy, not even close to the void between galaxies. You wouldn't have traveled far enough to see what real emptiness looks like. The void between galaxies makes our local space look crowded by comparison. If you shrank the Milky Way to the size of a dinner plate, the nearest galaxy, Andromeda, would be another dinner plate sitting 2 rooms away. Everything between them would be empty. Not mostly empty, empty. A few stray atoms drifting in the dark, so rare that you could travel for light years without detecting one. We've never seen the actual void with our naked eyes. We only know it exists through telescopes and mathematics. The darkness between the stars in our sky isn't the void. It's just the limit of our vision. The real emptiness is further out, deeper, darker than anything we can perceive by simply looking up. This creates a strange situation. Humans evolved looking at a crowded sky. We built our myths and navigation and sense of the cosmos around what we could see. But what we could see was profoundly misleading. It suggested a universe packed with stars, humming with light and energy. The reality is different. The universe is mostly nothing. And the parts that are something, the galaxies and stars and planets, are separated by distances so vast they might as well be in different realities. The question becomes, if space looks crowded from where we're standing but is actually empty, what does the real emptiness look like when you zoom out far enough to see it? Let's zoom out, see what happens to emptiness as we move through larger scales. Here in our local neighborhood, stars are roughly 5 light years apart. That's the distance light travels in 5 years, moving at 300 million meters per second. At that speed, you'd circle Earth 7.5 times in 1 second, and it still takes 5 years to reach the next star. The space between them isn't empty like a vacant room. It's empty like the gap between galaxies, just on a smaller scale. A few hydrogen atoms per cubic centimeter, some stray dust, mostly nothing. The Milky Way itself stretches 100,000 light-years from edge to edge. Picture our galaxy as a vast disk packed with 200 billion stars. That sounds crowded. It isn't. If you picked a random point inside the Milky Way and looked around, you'd see darkness in every direction. Stars would be visible, sure, but they'd be distant pinpricks. The space between them would dominate everything. Most of the galaxy is just that, space. Empty space separating islands of matter. The nearest major galaxy to us is Andromeda. It sits 2.5 million light-years away. The light you see from Andromeda tonight left before humans existed, before our ancestors came down from the trees, before anything resembling us walked upright. That's not looking at space. That's looking backward through time across an ocean of nothing. In our local group of galaxies, the average distance between each galaxy is about 3 million light-years. Think about that. 3 million years of travel at light speed just to reach your neighbor. The galaxies themselves are enormous, spanning thousands or hundreds of thousands of light-years. But the gaps between them make the galaxies look like specks of dust in an empty cathedral. The ratio shifts. It's no longer mostly empty. It's almost entirely empty. Between galaxy clusters, the distances grow even larger. 10 to 50 million light-years of nothing, just void. When you reach true intergalactic space, the density of matter drops to roughly 1 hydrogen atom per cubic meter. 1 atom in a space the size of a small bedroom. Compare that to Earth's atmosphere at sea level, which contains 10 to the power of 25 atoms per cubic meter. The density difference between intergalactic space and the air you're breathing is the same as the difference between air and solid steel, except backwards. Space is that much more empty than air. Here's what makes this strange. The space between galaxies isn't just empty of stars. It's emptier than any vacuum we've ever created in a laboratory. The best vacuum chambers on Earth still contain billions of atoms per cubic centimeter. We pump out the air, seal the chamber, remove every molecule we can detect. Billions still remain. Intergalactic space has less than 1 atom per cubic meter. We literally cannot create emptiness that empty. Our technology can't reach it. Our experiments can't simulate it. The void between galaxies exists in a state of emptiness we can only describe mathematically. Consider the local void, a region of space near our own cosmic neighborhood. If Earth were a grain of sand, the local void would be large enough to contain every beach on Earth with room left over for every desert. That's not an exaggeration. That's the actual scale. And the local void isn't even considered particularly large. It's just one of many such regions scattered throughout the observable universe. There's something else. The Boötes void, one of the largest known empty regions, spans 330 million light-years across. Light from one side of the Boötes void left before the dinosaurs existed and still hasn't crossed to the other side. The tyrannosaurs walked and hunted and went extinct. The asteroid fell. The mammals rose. Humans evolved, built civilizations, invented telescopes, and that light is still traveling through empty space, not yet halfway across the void. This is what normal intergalactic space looks like. This is the baseline. 1 atom per cubic meter. Distances measured in millions of light years. Emptiness so complete that our most advanced technology can't recreate it. That's the standard emptiness of the universe, the regular void between galaxies. Which raises a question. If this is what normal looks like, what are cosmic voids? The Boötes void is a spherical region of space, 330 million light-years across. That distance is so large that light which left one edge before the first dinosaurs evolved still hasn't reached the other side. The Triassic period began. Pangaea broke apart. The asteroid fell. Mammals diversified. Primates emerged. Every step of human evolution from ape-like ancestors to modern civilization. That light is still crossing empty space, and it's crossing through almost nothing. The Boötes void contains approximately 60 galaxies. In a normal region of space that size, you'd expect to find 10,000 galaxies. The void has less than 1% of what should be there. Picture the cosmic web like someone threw a handful of sand at a wall, most of it clumped in spots, stuck together in patterns, but most of the wall stayed empty. That's the structure of the universe. Matter gathered in threads and sheets. Everything else became void. Astronomers discovered the Boötes void in 1981. They called it the Great Nothing. The name fits. The void isn't just emptier than normal space. It's emptier than the space between galaxies we explored in the last section. Remember, regular intergalactic space has about 1 atom per cubic meter. The Boötes void has 10 to 20% of even that sparse density. It's empty in a way that makes normal emptiness look crowded. Think about it this way. If you started counting stars in the Boötes void when your great-grandparents were born, counting 1 per second, never stopping, you'd finish before you retired. Your entire working life would be enough to count every star in a region 330 million light-years across. Do the same thing in a normal patch of space that size, and your descendants 300 years from now would still be counting. They'd pass the task down like an inheritance, generation after generation, counting stars, never reaching the end. The Boötes void isn't alone. We've mapped thousands of voids throughout the observable universe, some smaller, some larger. The local void, relatively close to us, spans 150 million light-years. The giant void in Canes Venatici reaches 300 million light-years, just like Boötes. These aren't rare anomalies. They're the dominant feature of cosmic structure. Voids make up about 80% of the universe's volume. Read that again. 80%. The galaxies, stars, planets, everything we can see, all of it exists in the remaining 20%. We live in the walls and filaments wrapped around bubbles of nothing. The cosmic web isn't a web of matter with empty spaces between. It's a web of empty spaces with thin threads of matter defining the edges. This structure extends everywhere we can observe. Galaxies cluster into walls and filaments. These structures wrap around voids like soap film around air bubbles. The walls themselves are thin, relatively speaking. Most of the volume belongs to the voids. The Sloan Great Wall, one of the largest structures we've found, stretches 1 billion light-years, but it's a sheet of galaxies surrounding empty space. The wall exists because the void exists. The emptiness defines the structure. You might think of voids as just gaps, regions where galaxies never formed, cosmic deserts left behind when matter gathered elsewhere. That's not quite right. Voids aren't passive absences. They're active, dynamic. They're doing something. They're growing. Right now, every void in the universe is expanding. The Boötes void is larger today than it was when we discovered it in 1981. Not because we measured it wrong the first time, not because we've refined our instruments, but because it literally grew. The void expanded during the decades between that first observation and now. The walls of galaxies surrounding it moved farther apart. The emptiness increased. All voids do this. They expand, pushing galaxies at their edges outward. The local void near us is growing. The giant void in Cain's Venatici is growing. Every spherical bubble of nothing in the cosmic web is inflating, making itself larger, increasing the distance between the galaxies in its walls. The universe isn't just empty, it's getting emptier. Dark energy drives this expansion. The same force stretching space between galaxy clusters also inflates voids from within. Consider the timescale. Dark energy pushes galaxies apart faster than evolution created every species on Earth. The entire tree of life emerged in less time than it takes for a void to double in size. From the first bacteria to humans, all of biological history happened quicker than a void's expansion cycle. Think about that. Life arose, diversified into millions of forms, developed intelligence, built civilizations, and cosmic voids barely noticed. The expansion is accelerating. Voids grow faster now than they did 1 billion years ago. They'll grow faster still 1 billion years from now. The walls between voids are thinning. The filaments of galaxies are stretching. Eventually, given enough time, the voids will dominate so completely that the walls separating them will dissolve. Galaxies will drift into isolation. The cosmic web will unravel. But we're not there yet. For now, we exist in the walls. We live in the structure surrounding emptiness. The Milky Way sits in a filament between voids. We're part of the foam, not the bubble. And from here, we can look out into the voids and see their edges. We can measure their size. We can watch them grow. The Boötes void sits 330 million light-years away. Its nearest edge is farther than anything you can see without a telescope. You can't point to it in the night sky and show someone where it is, but it's there. A sphere of almost nothing, spanning a distance light takes 300 million years to cross. 60 galaxies lost in a space that should hold 10,000. And it's expanding, even as you read this, pushing its boundaries outward, claiming more volume, increasing the emptiness. Which raises the obvious question, what makes them grow? What force could inflate these massive regions, pushing galaxies away like debris on a shockwave? The answer involves a fight between two fundamental forces, one that pulls everything together, and one that tears everything apart. Gravity pulls things together. That's the simple version. The one we all learn in school. Drop a ball, it falls. Throw it up, it comes back down. The Earth orbits the Sun because gravity holds it there. The Sun orbits the center of the Milky Way because gravity keeps it on track. Every piece of matter in the universe attracts every other piece of matter. The more mass something has, the stronger it pulls. The farther away it is, the weaker that pull becomes. This works beautifully on small scales. Small, in cosmic terms, means anything up to a few 100 million light-years. Planets stay bound to their stars. Stars cluster into galaxies. Galaxies gather into groups and clusters. Gravity is the force that builds structure. It's why we have solar systems instead of scattered rocks. It's why we have galaxies instead of lonely stars drifting through infinite darkness. Without gravity, the universe would be a featureless fog of atoms, spreading thinner and thinner forever. But gravity has limits. Its strength falls off with distance, following what physicists call the inverse square law. Double the distance between two objects, and the gravitational force drops to 1/4. Triple it, and the force becomes 1/9. By the time you're talking about distances of hundreds of millions of light years, gravity between separate galaxy clusters becomes almost negligible. It's still there, technically, but it's weak, too weak to hold things together against what's pushing them apart. Picture gravity like trying to hold hands in a crowd that's running away from a fire. You can grip your immediate neighbors. Your fingers lock. You pull them close. But everyone else, the people 10 rows back, they're already gone. You'll never reach them. The crowd is moving too fast. Gravity works the same way. It can hold galaxies together in clusters. It can keep those clusters bound to each other if they're close enough. But across the vast distances of cosmic voids, it loses its grip entirely. That's where dark energy enters the picture. Dark energy is the opposite of gravity. It doesn't pull things together, it pushes them apart. More accurately, it expands the space between things. It's not a force in the traditional sense. It's a property of space itself. Every cubic meter of empty space contains dark energy, and the more space you have, the more dark energy you have, which means the more space expands, the more dark energy there is to make it expand faster. Think of dark energy like interest on a loan. The more debt you have, the faster your debt grows. Eventually, the interest compounds. The growth itself starts growing. You're not just paying back what you borrowed anymore. You're paying back the growth of the growth. Dark energy works the same way. The more space exists, the more dark energy exists. The more dark energy exists, the faster space expands. The faster space expands, the more new space gets created. It's a runaway process, self-reinforcing, accelerating. Here's the critical part. Dark energy is incredibly weak on small scales. Inside a galaxy, gravity dominates completely. The dark energy present in the space between stars is far too weak to overcome the gravitational binding holding the galaxy together. Same goes for galaxy clusters. Even across millions of light years, if there's enough matter, gravity wins. But above a certain scale, about 200 million light years, dark energy takes over. 200 million light years. That's the distance light travels in 200 million years, moving at 186,000 miles per second. If you left Earth when the first dinosaurs appeared and traveled at light speed, you still wouldn't have covered that distance yet. At these scales, there's not enough matter to generate sufficient gravity. The space is too vast. The mass is too diffuse. Dark energy, spread across all that volume, becomes the dominant force. And in cosmic voids, where matter is already sparse, dark energy doesn't just dominate. It rules completely. The voids are like clearings in a forest where the trees can't grow because the soil itself pushes seeds away. It's not that nothing landed there. It's that the ground actively rejects roots. Matter can't accumulate in voids because the space won't let it. This is why voids grow. Inside a void, you have enormous volumes of space with almost no matter. Very little matter means very little gravity. Very little gravity means dark energy faces no opposition. So the space expands, and as it expands, more dark energy comes into existence, which makes the expansion accelerate, which creates even more space. The void gets bigger, not through any external force, but through internal growth. It's expanding from within. Here's the part that most people get wrong. The galaxies aren't moving away from the center of a void. There is no center. The void doesn't have a point it's expanding from, like an explosion. The galaxies in the walls surrounding a void aren't racing outward through space. They're essentially standing still. It's the space between them that's growing. New space is being created in the gaps. The void inflates like a balloon, but the galaxies on its surface aren't moving. They're just getting farther apart because there's more distance between them than there was before. This means the expansion isn't motion, it's creation. Space itself is coming into existence inside the void. Every second, the void contains more cubic light years than it did the second before, and every one of those new cubic light years contains dark energy, which pushes the expansion faster. The void becomes a runaway engine of emptiness. The emptier it gets, the faster it grows. The faster it grows, the emptier it becomes. This is the fundamental mechanism behind cosmic voids. Gravity builds structure on small scales. Dark energy tears structure apart on large scales. And in the voids, where there was already little structure to begin with, dark energy wins completely. These regions don't just lack galaxies, they actively resist them. Any matter that wanders too close gets swept up into the walls by the gravitational pull of the denser regions surrounding the void. The void itself keeps expanding, claiming more volume, pushing its boundaries outward into what used to be normal space. The Boötes void is doing this right now. So are the thousands of other voids scattered throughout the observable universe. They're all growing, all accelerating, all creating new space where there used to be less. And the universe, already 70% empty, is becoming emptier with every passing moment. So what is this force that's driving everything apart? What exactly is dark energy? Here's what we know for certain. Dark energy makes up 68% of everything that exists. Dark matter accounts for 27%, and normal matter, the atoms that make up stars and planets and you and me, is just 5%. 5%. Everything you've ever seen, every photograph from space, every galaxy in every telescope image, all of it is a rounding error in the cosmic budget. If the universe were a corporation, dark energy would be the majority shareholder with 68% ownership. Dark matter would have 27%, and everything we can see, every star and planet and galaxy, would own 5% and have no voting rights. We're not just the minority, we're a tiny minority with no say in what happens next. The thing is, we can measure dark energy with remarkable precision. We know how much of it there is. We know its density, about 6 times 10 to the negative 10th joules per cubic meter. That number doesn't mean much until you picture it differently. The energy density of dark energy is equivalent to one hydrogen atom in a volume the size of Earth. One single atom spread across the entire planet. That's how diffuse it is. And yet, this unimaginably weak energy dominates the fate of the entire universe. Think about that for a second. Something so sparse, so thin, so utterly negligible on human scales that we'll never detect it in a laboratory. It decides what happens to galaxies. It determines whether the universe expands forever or collapses. It's the majority shareholder, and it doesn't even register in our daily lives. Dark energy is like air pressure. You don't notice it. You walk around in it every day without feeling a thing, but it's strong enough to crush a metal barrel if you remove the air inside. The absence reveals the force. The same goes for dark energy. We don't feel it locally, but remove it from the cosmic equation and everything falls apart. The math doesn't work. The observations don't make sense. The universe we see couldn't exist. We first found evidence for dark energy in 1998. Astronomers were studying distant supernovas, trying to measure how fast the universe was expanding. They expected to find that the expansion was slowing down, pulled back by gravity over billions of years. Instead, they found the opposite. The expansion was speeding up, getting faster over time, not slower. That discovery changed everything. It meant something was pushing outward, overpowering gravity on the largest scales. Something invisible, something that didn't interact with light, something that filled all of space. They called it dark energy because they had no idea what else to call it. Here's what makes dark energy different from anything else we know. It doesn't clump. Dark matter clumps into halos around galaxies. Normal matter clumps into stars and planets. Dark energy spreads evenly through space, a uniform field that never concentrates, never gathers, never pools. It's the same density everywhere, in every direction, at every point in the universe. It doesn't interact with light. You can't see it, photograph it, or detect it with any electromagnetic radiation. It's not made of particles, as far as we can tell. It doesn't emit, absorb, or reflect anything. And here's the strangest part. It doesn't dilute as space expands. When normal matter spreads out over a larger volume, its density drops. You take a kilogram of matter and stretch the space it occupies, you get less matter per cubic meter. That's just basic physics. Dark energy doesn't work that way. As the universe expands, the energy density stays constant. More space means more dark energy. The total amount increases as the volume increases. That's not how matter behaves. That's not how energy usually behaves. That's something else entirely. The leading theory is that dark energy is vacuum energy, the energy of empty space itself. Quantum mechanics tells us that even a perfect vacuum isn't truly empty. Particles pop in and out of existence constantly, borrowing energy from nothing and paying it back before the universe notices. Those quantum fluctuations have energy, and if space itself has energy, then creating more space means creating more energy. The density stays constant because space and energy are tied together. That's the theory anyway. The honest answer is we're not sure. This is the part that gets me. We've mapped the universe. We've measured its expansion. We've calculated how much dark energy there is down to multiple decimal places, and we still have no idea what we're measuring. It's like weighing an invisible object by watching things move around it. You know exactly how heavy it is, but you've never actually seen it, touched it, or understood what it's made of. We're astonishingly good at describing what dark energy does. We're completely clueless about what it is. We don't know why it exists. We don't know why it has the specific strength it does. And here's the part that should keep you up at night. If dark energy was slightly stronger, galaxies would never have formed. Atoms would be ripped apart faster than gravity could pull them together. The universe would be nothing but isolated particles flying away from each other at increasing speeds. No stars, no planets, no life. If dark energy was slightly weaker, the universe would have collapsed back on itself billions of years ago. Gravity would have won. Everything would have crunched back down into a hot, dense state before the first stars even formed. We exist in a razor-thin range of possible dark energy strengths. Too much and structure never forms. Too little and the universe dies young. We happen to live in the narrow band where galaxies can exist, where stars can shine long enough for planets to cool and life to emerge. We have absolutely no idea why. Nobody does. There's no theory that predicts the exact strength of dark energy. There's no explanation for why the value is what it is and not something else. It just is. We measure it. We observe its effects, and we shrug. The universe is 68% dark energy, and 68% of the universe is something we don't understand at all. We can track its effects perfectly. We can watch galaxies accelerate away from each other because of it. We can calculate how much faster the expansion will get over the next billion years, but we can't tell you what we're tracking. Let's take a step back for a moment. We've been talking about what dark energy does, how it stretches the universe, how it governs the future of everything. But how do we actually know any of this? How did we discover that the universe is accelerating toward emptiness? The answer takes us back to 1998. Two teams of astronomers working independently were studying exploding stars. They weren't looking for dark energy. They didn't even believe dark energy existed. They were trying to measure how fast the universe's expansion was slowing down. Everyone assumed it was slowing down. Gravity pulls everything together. The universe has been expanding since the Big Bang, sure, but all that matter should be putting the brakes on. Every galaxy pulling on every other galaxy. The expansion should be decelerating. The only question was how much. One team was called the Supernova Cosmology Project, led by a physicist named Saul Perlmutter. The other was the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. They were competitors, both racing to make the same measurement, both using the same method. They were looking for Type Ia supernovae. These are explosions of white dwarf stars. When a white dwarf accumulates enough matter from a companion star, it hits a critical mass and detonates. Every single one explodes at almost exactly the same brightness. They're called standard candles. You know exactly how bright they should be, which means you can tell how far away they are. Think of it like this. You know exactly how bright a 100-watt light bulb is. If you see one that looks dim, you know it must be far away. If it looks really dim, it's really far away. The math is simple. Brightness drops with distance in a predictable way. Type Ia supernovae are bright enough to see across billions of light years. They're perfect for measuring cosmic distances. You find one, you measure how bright it appears, and you calculate how far away it must be. Then you look at how fast its galaxy is moving away from us. That tells you how fast the universe was expanding when that light left the supernova. Both teams found dozens of these supernovae. They measured them carefully. They did the calculations, and the supernovae were dimmer than expected. Not just a little dimmer, significantly dimmer, which meant they were farther away than they should be. The universe had stretched more than the models predicted while their light was traveling toward us. The expansion wasn't slowing down, it was speeding up. Imagine watching a ball roll up a hill. You expect it to slow down, maybe roll back toward you. Instead, it accelerates. It launches into the sky. It violates everything you think you know about how things work. That's what the data showed. The universe was accelerating. Both teams thought they'd made a mistake. The Supernova Cosmology Project spent months checking their instruments. The High-Z team recalibrated everything. They looked for systematic errors, for ways the dust between galaxies might be dimming the light, for any explanation that didn't require rewriting cosmology. They couldn't find one. The data kept saying the same thing. Expansion is accelerating. Something is pushing the universe apart, overpowering gravity, and that something is getting stronger over time. They called it dark energy because they had no idea what it actually was. They still don't. When the teams finally went public, many cosmologists were skeptical. The claim was too big, too strange. It took years of additional observations, from telescopes on the ground and in space, to convince the broader scientific community. By the mid-2000s, the evidence was overwhelming. The universe is accelerating. Dark energy is real. In 2011, Perlmutter, Schmidt, and Rees won the Nobel Prize in Physics. The discovery changed everything. Before 1998, we thought the universe would eventually collapse back on itself, or at least coast to a stop. After 1998, we knew it would expand forever, faster and faster, until everything disappeared beyond every horizon. We live in one of the first human generations to know this. Everyone before 1998 had a different picture of the future. They thought the universe might be cyclic, collapsing and rebirthing in an endless rhythm. Or they thought it would expand forever, but gently, asymptotically, approaching stillness. They were wrong. The supernovae those teams studied had light that traveled for billions of years. While that light crossed the universe, while it rode the expanding fabric of space toward Earth, entire mountain ranges rose and eroded away. Civilizations could have formed and vanished. The light kept coming, stretching to redder wavelengths as space expanded beneath it, carrying information about how fast the universe was growing. By the time it reached our telescopes, it was telling us something we didn't want to hear. The universe isn't just expanding, it's accelerating away from itself, and there's no mechanism to stop it. That's how we know. Not from theory, not from philosophy, from measuring the faint light of exploding stars and doing the math. The universe told us its fate, and we finally learned to listen. The universe is accelerating apart. That discovery was just the beginning, because once you know the expansion rate, you can calculate something more fundamental. You can figure out what shape the universe actually is. This isn't metaphorical shape. The universe has a geometry, real curvature, that determines its fate. There are three possibilities. Each one leads to a different ending. The first is a closed universe. Picture the surface of a sphere. If you lived in a closed universe and traveled in a straight line for long enough, you'd eventually come back to where you started. The universe would curve back on itself, finite but with no edge. Travel far enough in one direction and you'd see the back of your own head, given enough time. A closed universe would be packed with enough matter that gravity would eventually win. The expansion would slow, stop, then reverse. Everything would collapse back into a single point. The big crunch. The second possibility is an open universe. This one has negative curvature, like a saddle. The geometry bends outward instead of inward. An open universe is infinite. Travel in any direction forever and you'll never return. You'll just keep going through new space that stretches on without end. Open universes expand forever. Gravity can't stop them because there isn't enough mass to pull everything back together. The third option is a flat universe. Zero curvature. Euclidean geometry, the kind you learned in school. Parallel lines stay parallel forever. A flat universe is also infinite, but it sits right on the knife edge between closed and open. It expands forever, but just barely. Without dark energy, a flat universe would slow down asymptotically, approaching but never quite reaching a standstill. Which one do we live in? That depends on density. There's a critical density for the universe, about 5 hydrogen atoms per cubic meter, averaged across all of space. That includes the voids, the galaxy clusters, everything. 5 atoms per cubic meter is almost nothing. A single breath contains more matter than a cubic kilometer of space at critical density. But that's the threshold. If the universe's actual density is higher than critical density, it's closed. If it's lower, it's open. If it matches exactly, it's flat. We've measured it. The universe is flat. Not approximately flat. Flat to within 0.4% margin of error. The measurements keep getting more precise, and they keep showing flatness. This is deeply strange. There's no reason the universe should be flat. Closed and open are just as valid mathematically. The laws of physics don't prefer one geometry over another. It's like flipping a coin and watching it land perfectly on its edge, then flipping it again and having the same thing happen. And again, every measurement, the coin lands on its edge. Here's the honest answer. We don't really know why the universe is flat. We have theories. Inflation is the leading candidate. That's the idea that the universe expanded exponentially in the first tiny fraction of a second after the Big Bang. Inflation would naturally flatten any initial curvature, the way inflating a balloon makes its surface look flatter the bigger it gets. But we don't know for sure, and that bothers cosmologists more than they usually admit. Because flatness isn't just a minor detail. It's a fundamental property that seems weirdly fine-tuned, and physics doesn't like fine-tuning. Fine-tuning usually means you're missing a deeper explanation. The flatness means the universe is infinite. Space goes on forever, in all directions. There's no edge, no boundary, no center, just endless space with matter distributed through it in an ever-expanding web. And we're not just flat, we're flat with dark energy. That's the worst combination. A flat universe without dark energy would expand forever but decelerate over time. Structure could still form. Galaxies could still merge. Things would spread out, but slowly, gently. We don't get that. We get a flat universe with dark energy pushing everything apart faster and faster. The critical density knife edge that we're balanced on, dark energy tilts it toward endless acceleration. We have infinite space, and we have accelerating separation, both at once. Think about what that means for the voids. They're already the largest structures in the universe, hundreds of millions of light years across, nearly empty, just a few lonely galaxies drifting through darkness. Those voids are growing. If you could watch a single void expand for your entire life, 80 years of continuous observation, it would grow by a distance greater than the width of our solar system. Not the distance to the nearest star, the whole solar system, from the Sun out past Neptune. That much expansion in one human lifetime. The voids are winning. In a flat universe with dark energy, they'll eventually consume everything. Galaxy clusters will become isolated islands, then individual galaxies. Then nothing will be able to see anything else. Just darkness in all directions, expanding without limit. The geometry isn't just an abstract property. It determines what happens next. And what happens next is separation. Endless, accelerating, irreversible separation. The universe told us it's flat. The measurements are clear. What we still don't understand is why. Why this particular geometry? Why this perfect balance between expansion and density? Why does the coin keep landing on its edge? Those questions lead somewhere uncomfortable. Because if the flatness is fine-tuned, if it requires specific initial conditions we can't explain, then maybe the early universe wasn't random at all. Maybe there's a reason things started the way they did. Or maybe we're just extraordinarily lucky. And luck that good should make you suspicious. The voids aren't just growing in our particular patch of space. If the universe is truly flat and infinite, then there are voids everywhere, endless regions of nothing, all expanding, all pushing matter into thinner and thinner filaments. The geometry guarantees it. Flatness plus dark energy equals a future where emptiness dominates. We live in the era when galaxies still cluster together, when light can still travel between them, when the universe still looks full, if you don't look too closely at what's between the stars. That era is ending. Remember when we said voids are just big, empty regions between galaxies? That was true, but incomplete. Voids are something else too. They're time machines, not in the science fiction sense, in a more unsettling way. They show us what the entire universe will look like, not in some distant abstract future, eventually. Think of voids like the first grey hairs showing up decades before old age. They're a preview of an inevitable future state. that will eventually consume everything. The emptiness isn't coming. It's already here. It's just concentrated in specific regions. For now, voids are growing. They've always been growing, but the rate is accelerating. A typical void expands by roughly 10% per billion years in diameter. That doesn't sound dramatic until you realize the expansion is speeding up. Dark energy becomes more dominant as the universe ages. The force pushing space apart gets stronger relative to everything else. Voids don't just grow, they grow faster every billion years that passes. Right now, voids occupy about 80% of the universe's volume. 80%. Most of the universe is already empty. The cosmic web, all those filaments and clusters where galaxies live, fills only the remaining 20%. We live in the minority, in the leftover space, in the parts that haven't been claimed by nothing yet. Run the math forward. In 100 billion years, voids will occupy 95% of the universe's volume. The filaments will be thinner, the clusters more isolated, the islands of matter drifting farther apart in an ocean of expanding emptiness. In 1 trillion years, voids will fill 99.9% of everything. The cosmic web won't exist anymore, just isolated galaxy clusters, each one alone in its own expanding bubble of void, each one an island with no neighbors, no bridges, no way across. Picture the universe as a handful of rice thrown at a wall. Most grains stick together in spots, little clumps scattered across the surface, but most of the wall stays empty. That's the cosmic web right now. The clumps are galaxy clusters. The empty wall is voids. Over time, gravity pulls each clump tighter while dark energy pushes the clumps farther apart. Eventually, every clump becomes an island. The wall between them keeps growing. Structure formation in the universe ended roughly 6 billion years ago. No new galaxies are forming anymore. Existing ones just evolve. They merge with neighbors. They consume smaller galaxies. They burn through their gas and gradually fade, but no new ones appear. The universe stopped making galaxies when dark energy became dominant. When expansion started accelerating, the voids won. They claimed the future. Now, they're just asserting that claim across more and more space. The universe has entered its final configuration. There's a pattern now, and that pattern is set. Matter clusters here, voids expand there. Everything from this point forward is just playing out the consequences. The galaxies we see are the last generation. They'll last trillions of years. But when they're gone, nothing replaces them. Voids aren't the future. They're the future asserting itself in the present. Regions where the universe's ultimate state has already begun, where the end game is visible now, if you know what you're looking at. The rest of the universe will catch up. It's just a matter of time. The universe's expansion works like writing a letter to someone who's moving away while your letter is in the mail. You send it. They keep moving. By the time the letter arrives, they're even more distant than when you started writing. You can never catch up. The destination keeps receding. That's what happens to light-crossing voids. The void expands while the light travels. The far side gets farther. The journey gets longer mid-journey. Here's the part that gets me. Voids don't just show us what the universe will look like. They show us what the universe is becoming right now. In real time, we observe voids by detecting the light from galaxies at their edges. That light takes millions of years to reach us, sometimes hundreds of millions of years. The light we see is old, outdated, a historical record. In the time it takes that light to travel from the edge of a void to our telescopes, the void has grown significantly. If a void is 500 million light-years across, and the light took 100 million years to reach us, that void has expanded by roughly 10% in the meantime. We're not seeing the void as it is. We're seeing the void as it was, a smaller, younger version. The current universe is already emptier than we can observe. Every void we measure is actually bigger than our measurements show. By the time we see them, they've moved on, grown larger, pushed galaxies farther apart. The observation lags behind reality. We're living in a universe that's ahead of its own appearance. You can't see the present universe, not all of it, not even close. The light hasn't arrived yet. The present state of distant voids is invisible to us. It won't become visible for millions of years. By then, those voids will have grown even larger. The present we finally see will be the past. Again, always. This is what we meant back at the beginning. The visible universe is an illusion. Not just because we only see a small shell around us. That's part of it. But there's another layer. We're not just looking at a small shell. We're looking at the past of a universe that's already more empty than what we're seeing. The measurements are wrong before we finish taking them. The universe moves on. Voids are time machines. They let us see the end state, the final configuration, the ultimate fate of everything. Not by showing us a distant future, by showing us a nearby present that's already farther along the timeline. The voids are what everywhere will look like when enough time passes, when dark energy has pushed everything apart, when the islands are too distant to see each other, when each cluster is alone. We live in the era when you can still see across voids, when light can still make the journey, when the cosmic web is still recognizable as a web. That era is ending, not quickly by human standards, quickly by cosmic ones. The voids are winning. They've always been winning. Now, they're accelerating. How long would it take to cross the Boötes void? Let's find out what happens when you try. The void is 330 million light-years across. That translates to 3.12 times 10 to the 24th power kilometers. Written out, that's 3 with 23 zeros after it. The number doesn't mean anything to human brains. We didn't evolve to process distances like that, so let's make it physical. Let's cross it. Start walking. Average human walking speed is about 5 kilometers per hour. You're moving, one foot in front of the other. At that pace, crossing the Boötes void would take 71 quadrillion years. That's 5 million times longer than the current age of the universe. The universe is 13.8 billion years old. You'd need 5 million complete universes, each one living and dying in full, to walk from one side of the void to the other. You'd walk through the birth and death of stars we can't imagine yet. You'd walk through the formation and collapse of galaxy clusters that will never exist. You'd walk until the concept of time loses meaning. Fine. Walking is absurd. Get in a car. Drive at highway speed, 100 kilometers per hour. You're moving 20 times faster now. It doesn't matter. You'd still be driving for 3.5 quadrillion years. The sun will die in 5 billion years. You'd outlast 700,000 suns. Every sun that dies, another one is born, lives its entire life, and dies again. 700,000 times, and you're still driving. Take a commercial airplane, 900 kilometers per hour. You're in the air, crossing continents in hours, oceans in half a day. Across the void, it takes 400 trillion years. The Milky Way will collide with Andromeda in 4 billion years. You'd witness that collision happen 100,000 times. Each time, the galaxies would merge, form something new, and the stars in that new galaxy would burn out completely. 100,000 collision cycles. The airplane is still in the air. Use Voyager 1. It's the fastest thing humans have ever built that's actually leaving the solar system. 61,000 kilometers per hour. It's been traveling since 1977. It's now in interstellar space, farther from Earth than any other human-made object. Point it at the Boötes void. It arrives in 5.6 trillion years, long after the sun dies, long after the Milky Way and Andromeda have finished their collision and settled into a new elliptical galaxy, long after every star you can see in the night sky has burned out, gone supernova, or collapsed into a white dwarf. Voyager would cross a graveyard. It would arrive at the far side of the void and find a universe that no longer resembles the one it left. Even at light speed, the fastest possible speed, allowed by physics, it takes 330 million years. Light left one side of the void when the first mammals appeared on Earth, small, shrew-like creatures hiding from dinosaurs. That light is still inside the void. It hasn't reached the other side yet. Mammals evolved into primates, into apes, into humans. We built civilizations, invented writing, went to space. The light is still crossing. It will keep crossing for another 200 million years. When it finally exits, Earth might not exist anymore. The sun will have begun its red giant phase. The inner planets will be gone. But here's the part that makes it truly impossible. While you're traveling, the void is growing. The universe is expanding. Space itself is stretching. If you tried to cross the void at any speed slower than light, the far side would recede faster than you're approaching it. You'd travel forward forever and never arrive. Picture walking up a down escalator. The escalator is moving faster than you can walk. You're moving. You're making progress. But the top is getting farther away. That's what happens below light speed. The void expands faster than you can cross it. At light speed, you'd make it. Barely. But at any speed slower than light, even Voyager 1, even close to light speed, the expansion wins. You can't get there from here, not even in principle. The void isn't just big, it's unreachable. There's a difference between distant and impossible. Distant means far away. Impossible means the laws of physics prevent arrival. For anything slower than light, the Boötes void is both. You could point yourself at the far side, accelerate to 99% of light speed, and still watch your destination slip away. The void grows by more distance than you can cover. You'd chase the horizon forever. This is what scale means at cosmic distances. Not just that things are far, that they're beyond crossing, that the universe has placed them in a category separate from reachable. You can imagine crossing them. You can do the math, but the math tells you no. The universe has drawn a line. On one side, places you can reach given enough time and speed. On the other side, places that expansion has locked away. The voids are on the far side of that line. Let's try to count them. The stars in the Boötes void, all of them. There are roughly 60 galaxies in the void. Each galaxy contains about 100 billion stars on average. That gives us around 6 trillion stars total. 6 trillion sounds like a lot. It is a lot, but compared to what should be there, it's almost nothing. In a normal region of space the same size, you'd find about 10,000 galaxies. That's 1 quadrillion stars. The void has less than 1% of what it should. But let's count them anyway. Let's say you could count 1 star per second, never sleeping, never stopping, just counting. In the Boötes void, you'd finish in 190,000 years. You'd start counting when the earliest cave paintings were being made. 35,000 years ago, humans were drawing bison on stone walls, and you'd be counting stars. You'd count through the entire span of recorded history, through every civilization that ever rose and fell. You'd still be counting today. You'd keep counting for another 150,000 years into the future. Every star in the void, 1 per second, takes nearly 200 millennia. That's for the void, the empty place. In a normal region of space, counting 1 star per second, you'd need 31 million years. You'd start before the asteroid hit, before the dinosaurs died. You'd count through their entire extinction, through the rise of mammals, through the evolution of primates, through the entire human story from beginning to end, and you'd still be counting long after we're gone. 31 million years to count what should be there. The void is so empty you could count every star in it in a single breath of cosmic time. Think about what that means. The difference between 190,000 years and 31 million years. That gap is the void. That missing time is the emptiness made real. You could count the void's stars in the time it takes for a species to emerge and vanish. But counting normal space takes longer than some evolutionary branches last. Let's shift the metric. Let's talk about heartbeats. A human heart beats about 3 billion times in an 80-year lifetime. From your first beat to your last, 3 billion. Every moment of your life, every breath, every thought, every dream. 3 billion heartbeats contain all of it. The number of seconds that light takes to cross the Boötes void is 10.4 times 10 to the 16th. That's 3 million human lifetimes worth of heartbeats. Every beat your heart ever makes, multiplied by 3 million. Every lifetime you could possibly live, stacked end to end 3 million times over. That's how long light travels through the void. Or try breaths. You take about 600 million breaths in a lifetime. Light crosses the void in enough time for 17 million lifetimes worth of breathing. Every inhale and exhale from birth to death times 17 million. The scale doesn't become more manageable when you make it human. It just becomes more impossibly empty. 330 million years ago, light entered the Boötes void from one side. It's still crossing. It won't emerge for eons yet, but let's talk about when it started. 330 million years ago, Earth was unrecognizable. This was the Carboniferous period. The continents were colliding to form Pangaea. The first reptiles were just emerging. Amphibians dominated. Insects grew to terrifying sizes. Dragonflies with 2-foot wingspans. Millipedes 8 feet long. The forests were different. Giant ferns and club mosses, some 100 feet tall. They'd fall and compress into the coal we burn today. And not a single flower had bloomed on Earth yet. Flowering plants didn't exist. Roses, daisies, orchids, sunflowers. None of them. No grass either. No fruit trees. No vegetables as we know them. Flowers wouldn't evolve for another 200 million years. When light entered the void, Earth was a planet that had never seen a bloom. That light has been traveling through emptiness longer than flowers have existed anywhere in the universe. I think about this sometimes when I'm standing outside at night. The light hitting my eyes left Andromeda before humans figured out agriculture. But that's nothing compared to the light crossing voids. That light left when Earth was unrecognizable. No grass, no flowers, no birds, no mammals, just ferns and insects and creatures we'd consider alien. And it's been traveling through nothing ever since. The photon didn't experience time. Relativity makes sure of that. But from our perspective, that photon has been alone in the dark for longer than complex life has existed on Earth. That's what voids do. They isolate light itself. And here's something most people don't realize. The photons crossing through voids right now are the most isolated objects in the universe. More isolated than anything else that exists. A photon crossing the Boötes void will travel for 330 million years without encountering a single atom in most cases. Not one collision, not one interaction, just empty space for the entire journey. For comparison, a photon traveling through Earth's atmosphere hits billions of atoms per centimeter. Billions. Every tiny fraction of distance. Constant collisions. That's why light scatters. That's why the sky is blue. A photon in normal intergalactic space might hit a few atoms during a similar journey. Not many, but a few. Space between galaxies is sparse, but not empty. There's hydrogen, helium, trace amounts of heavier elements. A photon makes the occasional contact, but a photon in a void can cross 330 million light-years and statistically hit nothing. The density is so low that interaction becomes vanishingly rare. These photons travel in darkness so pure we can barely comprehend it. They're more alone than anything else in existence, traveling through emptiness that approaches perfect vacuum. For hundreds of millions of years, they are isolated in a way that nothing on Earth, nothing in our solar system, nothing in our local galactic neighborhood can ever be. They are truly, completely alone, and they're everywhere in the voids right now. Billions upon billions of photons, each one on its own centuries-long journey through nothing. Each one crossing distances so vast that flowers could evolve, bloom, and go extinct while they travel. Each one experiencing zero time from its own perspective, but from ours, an eternity. That's what the void is. Not just empty space where galaxies should be, a place where even light becomes lonely. But what does empty actually mean? We call voids empty. We say they contain almost nothing. That's technically true, but it's also misleading, because nothing in the universe is truly empty, not even the voids. A void contains about 10 to 20% of the universe's average matter density. That sounds like a lot until you realize the universe's average matter density is already nearly nothing. Think of it this way. Earth's atmosphere at sea level is thick. You can feel it when you breathe. At 100 kilometers up, at the edge of space, there's still technically air, but it's so thin it might as well be vacuum. The density difference between sea level and the edge of space is similar to the density difference between normal cosmic space and a void. Still technically there, but so diffuse, it approaches meaninglessness. So what's actually inside a void? Dark matter, for one. We can't see it directly, but we can detect it through gravitational lensing. Light from distant galaxies bends as it passes through voids. Not much, but enough to measure, enough to know that dark matter exists there, creating subtle gravitational wells in the emptiness. The invisible scaffolding is present even where nothing else is. Then there's hydrogen gas, diffuse, spread so thin that calling it gas feels generous. We detect it through absorption lines. When light from a distant quasar passes through a void, certain wavelengths get absorbed by hydrogen atoms floating in the darkness. That's how we know the gas is there. Not from seeing it, from seeing what it takes away from light passing through. The amount of matter is almost incomprehensible in its scarcity. Picture a void the size of Earth, not Earth the planet, a spherical volume of space with Earth's diameter. If you could somehow gather all the hydrogen atoms, all the helium, all the matter floating in that Earth-sized void and compress it together, you'd have enough to fill a small swimming pool. That's it. An Earth-sized void compressed down to pool-sized matter. The rest is emptiness so pure, we have no earthly reference for it. The cosmic microwave background fills the voids too. These are photons left over from the Big Bang. They're everywhere in the universe. The voids aren't exempt. Temperature inside a void sits at about 2.7 Kelvin. That's the temperature of the cosmic microwave background itself. The photons are like the last light from a party that ended 13.8 billion years ago. The room is empty. Everyone went home, but the faint glow of old light still fills the space, still illuminates nothing. There are magnetic fields in voids, extremely weak but present. Generated by what? We're not entirely sure. Possibly from currents in the thin plasma, possibly from the early universe. They're so faint they barely register, but they exist. Neutrinos pass through constantly, billions of them. They interact with almost nothing. They were already ghostly in normal space. In a void, they're even more isolated, traveling through regions where interaction becomes statistically impossible. And then there's something stranger, virtual particles. Quantum mechanics predicts that even in perfect vacuum, particle and antiparticle pairs constantly pop into existence and annihilate each other. This happens everywhere. In your room, right now, in the space between atoms, and in the voids. The quantum foam of creation and destruction that underlies all of reality doesn't stop just because there's nothing else around. Even in the emptiest places in the universe, space-time itself seethes with temporary existence. But here's what we're learning. Voids might not be randomly empty. There's growing evidence that voids are partially empty because of what happened around them. When the first galaxies formed just outside void regions, their intense radiation and stellar winds created pressure. Massive stars lived fast and died young. Supernovae exploded. The energy from these events didn't just stay local. It pushed outward. It blew gas away from the proto-voids. It cleared out regions that might have otherwise accumulated some matter. This means voids might be partially artificial, not engineered by intelligence, but sculpted by the side effects of star formation billions of years ago. The emptiest places in the universe might be empty because the non-empty places pushed their matter away. Voids are defined as much by what's around them as by what's inside them. They're not passive, they're the consequence of everything else. The negative space carved out by structure formation. When galaxies pulled matter toward themselves, they also pushed matter away. The voids are where that pushed away matter never accumulated, where the gravitational competition between forming structures left gaps. So when we say a void is empty, we mean it's empty relative to its surroundings. We mean it lost the cosmic lottery of structure formation. We mean it's the space left behind when everything else gathered together. But it's not nothing. It's just the closest thing to nothing that exists on cosmic scales. And that raises a question. If voids aren't truly empty, what else might be happening inside them? The emptiest regions in the universe aren't quite empty. We've established that. They contain dark matter. They contain a few stray atoms. They contain the faint gravitational echoes of everything around them. But they also contain something else, something unexpected. galaxies. Not many, but they're there, scattered through the voids like forgotten islands in an endless ocean. These are void galaxies, and they're different from everything we've studied before. Most void galaxies are small, dwarf galaxies, in astronomical terms, the kind of galaxy that would barely register as significant in a dense region. But out here, in the void, they're all there is. They formed in isolation. They evolved in isolation. They never collided with a neighbor. They never merged with another galaxy. They never felt the tidal forces of a larger structure pulling them apart. Void galaxies are like humans who grew up in complete isolation. They developed differently because they never interacted with neighbors. No mergers, no collisions, no tidal disruptions. They're cosmically pure examples of how galaxies evolve in solitude. When we study them, we're seeing what galaxies look like when nothing interferes with their development. It's the control group for galaxy evolution. The differences show up in their chemistry. Void galaxies have lower metallicity than galaxies in dense regions. Fewer heavy elements, iron, carbon, oxygen, the stuff that makes planets and people. They have less of it. They also have younger stellar populations on average. More active star formation per unit mass. They're still making stars at a higher rate than you'd expect for their size. They haven't been stripped of their gas by interactions. They haven't exhausted their fuel. They're still burning. One example stands out. MCG plus 01-02-015. It sits in the void of Draco, one of the largest voids we've mapped. This galaxy is one of the most isolated objects known. The nearest significant neighbor is about 40 million light-years away. For context, our nearest large neighbor is Andromeda. It's about 2.5 million light-years away. We consider that a significant gap. Multiply that distance by 16. That's what a void galaxy experiences. The distance from a void galaxy to its nearest neighbor is like living in a house where your nearest neighbor is in another state. You can theoretically visit, but for all practical purposes, you're alone. There's no dropping by for dinner, no borrowing tools, no interaction at all. Just you, your house, and an unimaginable expanse of empty land in every direction. Most void galaxies sit 40 to 60 million light-years from anything else. Normal galaxies sit 2 to 3 million light-years apart. That's a factor of 20 times more isolated, 20 times less likely to ever interact with another structure, 20 times more alone. This isolation preserves them. When galaxies collide, they change, they merge, they trigger star formation, they disrupt each other's structure. Void galaxies never experience that. They're what galaxies look like when nothing happens to them, which makes them strange laboratories. We can study galaxy evolution without the noise of interactions. We can see the baseline, the default state, but voids themselves have other oddities. There are hints in the cosmic microwave background, cold spots, regions where the radiation from the early universe appears slightly cooler than average. Some of these cold spots might correlate with supervoids, the largest voids in the cosmos. The correlation isn't perfect. Scientists argue about the statistical significance, but if it's real, it tells us something about how voids affect light passing through them. This connects to something called the integrated Sachs-Wolfe effect. When light travels through a void, it experiences less gravitational influence than light traveling through dense regions. The void is expanding. The light falls into the void, gets a little blue shifted, then it climbs back out, gets a little red shifted. In a static universe, these effects would cancel out. But the universe isn't static, it's accelerating, so the cancellation isn't perfect. The light leaves the void slightly red-shifted compared to light that traveled through denser regions. This creates a temperature difference in the cosmic microwave background, a subtle signal, but it's there. Void galaxies sometimes show unexpected rotation patterns too. Their gas doesn't always rotate the way we'd predict. The dark matter halos around them seem shaped differently than halos in dense regions. These are small effects, hard to measure, but they suggest that even dark matter behaves differently in voids, that the environment shapes everything, even the invisible scaffolding of the cosmos. There's something else, something that doesn't get discussed much. A photon traveling through a void experiences less interference than you do walking across an empty room. In the room, you hit air molecules constantly, billions of collisions per second. The photon hits nothing for millions of years. It just travels, undisturbed, undeflected, pure motion through pure emptiness. It's the closest thing to frictionless travel that exists in nature, which brings us to a thought experiment. Imagine intelligent life evolves in a void galaxy. Not now, but billions of years from now, long after we're gone. Long after the Milky Way has merged with Andromeda and faded into red dwarfs. These future beings develop science. They build telescopes. They study their universe, and they see almost nothing. Maybe one galaxy, maybe two, faint smudges on the edge of detection. That's it. Their entire observable universe contains one or two other structures. Everything else is darkness. By that time, the universe will have expanded so much that the cosmic microwave background will be red-shifted beyond detection. They won't see it. They won't have evidence of the Big Bang. They won't be able to measure cosmic expansion. There won't be enough nearby galaxies to establish a Hubble flow. They'd likely conclude they lived in a small, static, mostly empty universe. One galaxy, maybe a companion or two, surrounded by infinite void. They'd be wrong, but they'd have no way to discover the truth. Every observation would confirm their limited picture. Every measurement would fit their model. They'd have a completely consistent, completely incorrect cosmology. Imagine being an astronomer in a void galaxy. You spend your entire career studying the cosmos. You build telescopes. You scan the sky, and you find almost nothing. One or two faint smudges, maybe. That's it. Your entire field of work is trying to understand a universe that appears to barely exist. Every grant proposal is essentially, please fund me to continue staring at darkness. And yet, you'd still be in a universe containing trillions of galaxies. You just couldn't see them. Geography is destiny, even on cosmic scales. We happen to live in an era and location where the universe can be studied. We live in a galaxy cluster. We live at a time when other galaxies are still visible. We live when the cosmic microwave background can still be detected. We live when cosmic expansion can still be measured. This window won't last forever. And in most of the universe, it doesn't exist at all. Future void civilizations won't have that luxury. They'll live in informational darkness. They'll ask the same questions we ask. They'll wonder about their origins. They'll wonder if they're alone. They'll wonder what lies beyond the darkness. But they won't be able to answer those questions. The evidence will be gone. Red shifted away, expanded beyond detection, lost to time and space, which makes you wonder, what are we missing? What's beyond our own detection limits? What truths about the universe are invisible to us? Not because they don't exist, but because we're looking from the wrong place at the wrong time? These questions about what we can't see point towards something even more fundamental. There's a boundary to what we can ever know, a line beyond which the universe becomes not just invisible, but unreachable. Cosmologists call it the cosmic event horizon. It sits roughly 16 billion light-years away. Beyond that distance, space is expanding faster than light can travel through it, which means nothing beyond that horizon can ever reach us, and we can never reach it. Think about what that means. The observable universe stretches 46.5 billion light-years in every direction. That's the radius of everything we can see, but the cosmic event horizon is much closer, 16 billion light-years. Most of what we observe is already beyond our reach. We can see about 2 trillion galaxies in the observable universe. That number gets repeated a lot. 2 trillion galaxies scattered across cosmic space. But if you left Earth today, traveling at the speed of light, how many could you actually reach? Not 2 trillion, not even close. You could reach galaxies in the local group, Andromeda, the Triangulum Galaxy, a handful of dwarf galaxies orbiting the Milky Way, maybe some nearby galaxy clusters if you're generous with the math. That's it. Everything else is already moving away from us faster than light can catch up. Picture this. If the cosmic event horizon were a fence around your property, every year someone would move the fence closer to your house. They'd take away more of your land. The boundary would creep inward, year after year, decade after decade. Eventually, the fence would be at your doorstep. Your property would be just your house and nothing else. No yard, no garden, just the structure you're standing in. That's what's happening to our cosmic neighborhood. The reachable universe is shrinking. The fence is closing in. Here's the part that sounds like a contradiction. We can see galaxies that are beyond the cosmic event horizon. Right now, through our telescopes, galaxies that are forever unreachable. How is that possible? If they're beyond the horizon, if space between us is expanding faster than light, how can we see them? The answer sits in the word see. We're not seeing those galaxies as they exist now. We're seeing their past. The light reaching us left those galaxies billions of years ago, when they were closer to us, before cosmic expansion pushed them beyond the horizon. That ancient light has been traveling toward us ever since, crossing space that was expanding, but not expanding fast enough yet to stop the light completely. So we observe their history. We see what they looked like when the universe was younger, when they were within reach, but we can never see what they look like now. We can never receive new information about them. We can never send a signal that would arrive. The connection is severed permanently. Every distant galaxy we observe is a ghost. We're looking at something that still exists, somewhere out there in space, but is forever cut off from us. The universe is filled with objects we can see, but never visit, never communicate with, never know anything more about than what their ancient light tells us. It's like people who moved away before social media existed. You have old photographs, letters they sent decades ago, memories of what they were like back then, but no way to find out what they're doing now, no way to reach them. Except, instead of choosing not to stay in touch, physics makes it impossible. The universe itself has cut the connection. There's another boundary worth mentioning, the Hubble radius, sitting at about 14 billion light years. That's the distance at which recession velocity equals the speed of light exactly. Not faster than light, exactly equal. It's slightly closer than the event horizon, and it marks a different kind of threshold. Beyond the Hubble radius, galaxies are receding from us faster than light, but light from those galaxies can still reach us, as long as they're not beyond the event horizon. The space the light travels through is expanding, but the light keeps making progress toward us, slowly, incrementally, like swimming upstream in a river that's flowing faster than you can swim, except the current gradually weakens as you go. The cosmic event horizon is like watching ships sail over the curve of the Earth. You're standing on a spherical ocean. The ships disappear over the horizon as they sail away, except in this case, the ocean itself is growing, and the horizon is getting closer to you. Every year, you can see less of the ocean. The curve moves inward. Eventually, it will reach your shore. The ships aren't just disappearing because they sailed away. The geometry of space itself is hiding them. This matters for what we can know. Most of the galaxies we can currently observe are already beyond the event horizon. We're studying their ancient light, building maps of the early universe, measuring their properties from billions of years ago. But the current state of those galaxies is unknowable. Not just unknown, unknowable. The information cannot reach us. It's not a technology problem. It's not a matter of building better telescopes. The universe doesn't allow it. We're trapped in an observable bubble, and that bubble, in practical terms, is shrinking. Not the observable universe itself. That will continue expanding. We'll continue seeing light from farther and farther away as photons from the early universe finally reach us. But the reachable universe, the part we could ever interact with or learn anything new about, is contracting. Galaxies that are near the edge of the event horizon today will slip beyond it tomorrow. Not literally tomorrow, but on cosmic timescales, soon, and once they cross that boundary, they're gone. We'll still see their old light for billions of years, but we'll never see them age, never see them evolve, never receive updates about what happened to them after they crossed the horizon. We're watching history that we can never update. The history we're watching won't ever update, but eventually, we won't even have that history to watch. In about 4.5 billion years, something will interrupt our view. The Andromeda Galaxy will collide with the Milky Way. Not a sudden crash. more like two clouds of stars drifting through each other over billions of years. Individual stars won't collide. The distances between them are too vast. But gravity will tear both galaxies apart and rebuild them into something new. 7 billion years after the collision begins, the merger will be complete. Astronomers call the result Milky Way, an elliptical galaxy, larger than either of its parents. All the stars from both galaxies mixed together into one massive structure. From a planet orbiting a star in Milky Way, the night sky will look different. More stars, no spiral arms, just a dense sphere of suns stretching in every direction. But outside that galaxy, darkness. Because by the time Milky Way forms, the universe will have expanded enough that most other galaxies will be unreachable. They'll still exist, but they'll be moving away so fast that their light will be stretched into invisibility, redshifted beyond detection. Fast forward to 150 billion years from now. Every galaxy outside the local group will have vanished from view. Not because they stopped existing, because the space between us and them expanded faster than light could cross it. Their light will be stretched into wavelengths so long that no instrument could detect them. The universe will look empty. One large galaxy, Milky Way, surrounded by absolute blackness. No distant galaxies, no cosmic web, no structure. Just one island of light in an ocean of nothing. Picture this. You live in a house where every window shows the same single lamp. Beyond that lamp, pure darkness. No stars, no glow on the horizon, no hint that anything else exists. The universe didn't end. It just hid itself. Astronomers living in that era will study their galaxy. They'll map its stars, measure its rotation, understand its structure. But they'll have no way to know there was ever anything else. No evidence of expansion. No distant galaxies to measure redshift from. No way to discover that the universe is growing. And it gets worse. The cosmic microwave background, the radiation left over from the Big Bang, will still be there. But by 1 trillion years from now, it will have redshifted so far that it becomes undetectable, stretched from microwaves into radio waves with wavelengths longer than galaxies. Background noise indistinguishable from nothing. The universe is like a library where the books slowly fade and disappear. Future civilizations will arrive at the library to find it empty. No way to know what knowledge was lost. No way to even know there were books. Those future astronomers will be brilliant. They'll have technology we can't imagine, but they'll be trying to reconstruct cosmology with no evidence. It's like being an archaeologist trying to study ancient Rome, except every artifact disintegrated, every text burned, every building crumbled to dust. Even the ground where Rome stood eroded into the ocean. You'd have to reconstruct history from nothing. They might theorize about a beginning. Some might propose that the universe had an origin and that it evolved from something different, but they couldn't prove it. No expansion to measure, no background radiation to detect, no distant galaxies to study. The universe would appear static, eternal, unchanging. They'd be wrong, but they'd have no way to know they were wrong. Think about what that means. The universe is erasing its own evidence, removing the clues that reveal its history. In the far future, cosmology won't just be difficult, it will be impossible, which makes our current era cosmically unique. We live in the brief period when the universe can be studied. Before now, in the early universe, things were too chaotic, too hot, too opaque to see through clearly. After now, in the far future, the evidence will be gone. We exist in a narrow window. That window spans a few 100 billion years, less than 10% of the star-forming era, less than 0.00001% of the universe's total timeline if it lasts forever. And we happen to be here, right now, when observation is possible, before galaxies merged into isolated islands, before the cosmic microwave background red-shifted into invisibility, before expansion carried all the evidence beyond reach. We're here when intelligent life can ask questions and find answers. If we're lucky to be here when observation is possible, that luck is either a remarkable coincidence or it suggests something deeper, something about the relationship between observers and observable universes. Maybe we're living in the only kind of era where beings capable of asking questions can find answers. Or maybe countless civilizations will arise in that far future. Brilliant minds asking the same questions we ask, staring at their one galaxy surrounded by darkness, building theories they can never test, wondering if they're alone not just in space, but in time. The universe won't tell them. It will have already erased the message. The message just got erased. What happens to the universe itself? The stars die first, not quickly. The universe keeps making new stars for another 100 trillion years. That's 10,000 times longer than the universe has existed so far. If the universe's current age were one day, we'd wait 27 years for the last sunset, 27 years of watching the same sky, knowing that when the last star finally ignites, that's it, no more light. The last stars die around 120 trillion years from now. Then, the degenerate era begins. Dead stars, black holes, brown dwarfs that never quite ignited, darkness with mass. The black holes persist longer, much longer. They sit in the void and slowly evaporate through Hawking radiation. A solar mass black hole takes 10 to the 67 years to disappear. A supermassive black hole at a galaxy's center takes 10 to the 100th years. These numbers don't mean anything at human scale. There's no comparison that makes sense. Just understand that it's longer than the time it took for stars to exist by a factor so large it has no name. The black hole era spans from about 10 to the 40th years to 10 to the 100th years. When the last black hole evaporates, even the darkness has mass anymore. Then comes the dark era. Only photons remain. Neutrinos, occasional positron-electron pairs that pop into existence from random quantum fluctuations, exist for an instant, then annihilate. The temperature of space approaches absolute zero, but never quite reaches it. Energy still exists, but it's spread so thin and so evenly that nothing can happen. No events, no change, just photons getting redder and redder as space expands. This endpoint has a name, heat death. It's driven by entropy, the second law of thermodynamics. Entropy always increases, always. Every event that happens, every star that burns, every thought you think, every breath you take increases the total entropy of the universe. Entropy is a tax on existence. Every event, every thought, every star pays the tax by increasing total entropy, and the universe collects until there's nothing left to take. The tax compounds. The debt comes due. Eventually, the universe reaches maximum entropy, perfect equilibrium. Heat death is like a cup of coffee cooling down forever. Eventually, the coffee, the cup, the room, and you all reach the same temperature. Nothing can ever happen again, because there's no energy difference to drive change. No heat flows from hot to cold, because there is no hot and cold. There's only one temperature. Work requires a difference, a gradient, something flowing from high to low. At heat death, everything is low. The gradient is zero. The universe still exists, technically. There's still space, still photons, but nothing happens, ever again. Nothing can happen. The voids we see now are previews. Remember when we said that? Back when we were looking at Boöte's void and the cosmic web, the voids are what everywhere becomes eventually. Cold, empty, dark, equilibrium. They're not aberrations, they're prophecies. The universe is practicing for its final state. I realize this is all tremendously depressing. We've gone from cosmic voids to the eventual thermal equilibrium of all existence, and I'm essentially telling you that everything ends in cold darkness or instant physics rewrite. This is why cosmology doesn't get invited to parties. But here's the thing. This is the most honest answer physics can give about ultimate fate. The universe doesn't care about being comforting. It just is what it is. And what it is, apparently, is temporary. But there's a darker possibility. Heat death takes 10 to the 100th years. That's slow. Inevitable, but slow. False vacuum decay is different. Our universe might exist in a metastable state, a false vacuum. It seems stable, like water cooled below freezing, but not yet frozen. But it's not the lowest energy state. If quantum tunneling creates a bubble of true vacuum anywhere in the universe, that bubble expands at the speed of light. Everything it touches gets converted to the new vacuum state. The physics change. The fundamental constants might shift. Atoms might not be stable anymore. Chemistry might not work. The electromagnetic force could be stronger or weaker. Particles could have different masses. This wouldn't just kill everything. It would rewrite the rules of reality itself. The worst part is we'd never see it coming. The bubble moves at light speed. Light from the bubble can't reach us before the bubble does. One moment, existence. Next moment, the physics that allows existence is overwritten. We wouldn't feel pain. We wouldn't feel anything. The neural processes that create feeling would stop being possible. It's probably not going to happen. The vacuum seems stable. We've been here for nearly 14 billion years, but we can't rule it out. The probability might be low, but it's not zero. Heat death is slow and inevitable. False vacuum decay is instant and possible. Those are the options physics gives us. Cold equilibrium after more time than has meaning, or instant rewrite with no warning. The universe doesn't offer comfortable endings. It offers honest ones. And honestly, everything ends. The only question is how and when. We're living in a narrow window. The universe is 13.8 billion years old. That sounds ancient. That sounds like forever. It's not. Stars will keep forming for about 100 trillion years. We're 0.01% of the way through that era. 1/100th of 1%. If the universe's timeline were a book, the era where stars exist would be the first sentence on the first page. And the rest of the book is blank pages in the dark. We're reading that sentence right now. Right now, voids make up about 80% of the universe. Eventually, that number approaches 100%. Structure is temporary. Emptiness is permanent. We exist in the flash of complexity between two eternities of nothing. One before the Big Bang. One after heat death. The voids aren't aberrations. They're the default state. Galaxies, stars, planets, us. We're the aberration. Think about what that means. We live in the only epoch where the universe can be studied. It's like having a library that's open for 1 hour in its entire existence, and we happen to walk in during that hour. We're not just lucky, we're impossibly lucky. The cosmic microwave background is still visible. Galaxies are still close enough to see. The expansion hasn't pulled everything beyond our light horizon yet. In the far future, astronomers won't have any of this. They'll look up and see almost nothing. No evidence of a Big Bang, no distant galaxies, just local stars slowly dying. They won't be able to reconstruct cosmic history. The evidence will be gone. We can. We're here at the moment when the universe still remembers its own beginning. The loneliest galaxy in the universe will drift in darkness for so long that the time humans have existed would fit into that duration like a single frame in a movie that runs for years. One frame. Blink and you'd miss it. That galaxy will spend more time alone than stars spent existing. More time in silence than matter, spent being interesting. The void reclaims everything. It always does. Here's the part that catches me. We're not separate from this story. We're not observers watching the universe from outside. We're made of the same atoms that will eventually spread into equilibrium. We're temporary patterns in matter, little complexity islands that exist because the universe hasn't reached heat death yet. Our thoughts, our discoveries, our understanding of cosmic voids. These are the universe observing itself before the observation becomes impossible. The voids aren't just out there. The void is our origin and our destination. We're the universe's brief dream of structure before it returns to sleep. And somehow, in this narrow window, we figured out what's happening. We mapped the voids. We measured the expansion. We calculated how long the light will last. We're temporary, but we're not ignorant. That has to count for something. You've never seen the real universe. Remember that. You've only seen the local structure, the stars in your sky, the galaxies in your telescope. You're looking at the exception, not the rule. The universe is empty. It's getting emptier. And we're living in the brief moment when empty isn't everywhere yet. Look up at the night sky tonight. Those stars are the exception. The void is the rule, and we're awake to see it.